Okay, so today I'm going to be going over replication forks and everything they have to offer for translation. And so if we're just going to start off, I have a replication fork on the board here. So that's what one looks like. And we have our 5' and our 3', and our 3' and our 5' labeled. We also have the whole basically 1 through 7, 1 through 8 steps for translation or transcription. So first we're going to start off by just saying what is the lagging and what is the leading strand. So the lagging and leading. So the lagging is always going to go 3' to 5', and our leading is going to go 5' to 3'. So this would mean that this, I'll bring you closer, this strand that's labeled 3' here, that would be our lagging. And this strand up here, that's 5', this would be our leading. And then same for over here, so this one that's 5', this strand would be our lagging. And this one's 5', so all of this would be our leading. So that is that. So now we're gonna go over these steps of transcription. So the first step here that we have on the board is that our initiator protein binds to the double-stranded DNA. So I'm gonna make a little blown up version here, over here. I'll bring you guys over in a second. Okay, so I have a little blown up version here of basically the sequence, but it's not pried apart yet. So our initiator proteins are going to bind to double-stranded DNA. So here, our initiator proteins are going to bind here. So that's going to be our initiator proteins. They're going to bind to each step. And then step 2, the double-stranded DNA is going to be pried apart by helicase. So helicase is going to come in. They're going to, so we have helicase right here. So this is helicase, the enzyme. And it is going to pry apart these. Step. And then that will form this. So they're going to be pried apart. So here they're connected together, and the initiator protein, the helicase, going to open them up and be pried apart for the replication fork. That's steps 1 and 2. And then for step 3, our single-stranded binding proteins are going to bind. So I already have them here. So our binding proteins sequences, they're going to bind to the protein. Now for a bit of confusing part from here on out, so step 4 is that our primase, which is an enzyme, begins replication and forms a primer. So what's going to happen here is primase is going to form a primer. I'll do here to here. So that's a primer right there. It's just a small section of 20 or less nucleotides sequence, small sequence. And then also for RNA, our Okazaki fragments are going to start there. So this is done by primase. Okay, and then step 5 is the nucleotides are going to add to the 3' end by DNA polymerase II, which is an enzyme, as well from 5' to 3' end. So, nucleotides. So this is going to be part of where our primer is added. So we're going to have, we'll make this a little smaller here. So this is going to be going to CAUG. So this guanine went to cytosine, this thymine went to adenine, this adenine went to uracil because we're doing RNA, and then this cytosine went to guanine. So everything's the same besides adenine going to uracil at this point. So we have that by DNA polymerase II. So DNA poly 2 will do this. And Okazaki fragments are going to finish at this point. Now for step 6, RNA primers are degraded by nuclease. So these RNA primers that we just wrote out, they're going to be degraded by nuclease. So we're going to come in and the fragments are going to be the same. Besides that uracil, which is the RNA primer, that is going to go to thymine, which what it would have been if there was no RNA primers. So then we have CATG for our primer sequence. And then for step 7, RNA nucleotides are replaced with DNA nucleotides. So we just did that here. So that's step 6 and step 7. So step 6, RNA primers are degraded by nuclease. So this is going to be my nuclease. RNA primers are degraded. And then I did step 7 where the RNA nucleotides are replaced with new ones. And then the Okazaki fragments are joined together and ligase is going to join the fragments together to end the process. So now I'm just going to show you some base pairs and what they would go to for lagging and leading. So if we did here, this would go to so this is going, so I'll do it over here. So this will go to A, U, C, G, A, U, C, G, A, U, C, G, C, A, U. So for the leading strand, we're gonna do the adenines to the uracil, and then for the lagging, so this would be the same. So T, A, G, C, T, A, G, C, T, A, G, C, T, A. So that would be the same for the lagging. So if we were to do this lagging strand, finish it, it would be A, T, G, C, A, T, and G. So A is going to go to T, T is going to go to A, C is going to go to G, and G is going to go to C for DNA. And for RNA, A is going to go to U, T is going to go to A, C is going to go to G, and G is going to go to C. So that's the only difference in RNA is adenine is going to go to uracil. So that is transcription.